All right, welcome to the video. In this video, we are going to discuss our previous lesson revolving around dissolution and how that compares to dissociation, including that with this concept of colligative properties. Now, before we discuss colligative properties, we need to quickly revisit the difference between dissolution and dissociation. Dissolution, it just means being dissolved or coated in water. And what we talked about is how something like sucrose or sugar behaves much differently in water than something like sodium chloride. Ultimately, what we found is that something that is covalent, like sugar, does not dissociate or split apart into individual ions in water, whereas something like sodium chloride, an ionic compound, does. Electrolytes dissolve and dissociate, whereas non-electrolytes will or might dissolve, but they don't dissociate. So this is a concept or an idea that we're going to want to keep in mind as we begin to talk about these colligative properties. Now, colligative property is a property of a solution that depends on the concentration of solute molecules or ions, but not on the identity of the solute. So essentially, what we're talking about here is the amount of solute that we add, or the concentration of the solute that we add, has a large influence over things like freezing point, where we all know here in the Midwest, we add salt to our roads or sidewalks in order for that ice to melt, so that way we're not slipping and breaking our skulls open. We also have seen maybe in our everyday lives that we add salt to our water when we want to boil it for the purpose of making pasta, rice, or anything for that matter when you need water to boil. And to be quite honest, we're not adding salt to the water so that our pasta can be salty. We're doing that so we can influence or change the boiling point of that water. So these colligative properties, or what we're talking about here, is ways that we can either make ice freeze at a lower temperature or make water boil at a higher temperature. So before we get into that, we have this thing or this variable called the Van Hoff factor. Basically, the Van Hoff factor is the number of particles into which a solute dissociates. So when we did our dissociation equations in class, what we were doing was we were setting ourselves up to be able to identify this Van Hoff factor, or just the number of ions that are produced as these compounds dissociate or do not dissociate. So we have some examples here, like NaCl, sodium chloride, salt. When that is an ionic compound, so when it dissociates into a sodium and a chlorine ion, we've produced two ions or two particles in that dissociation. Whereas something like CaCl2, also an ionic compound, produces one calcium and two chlorine ions. 1 and 2 gives us 3 total particles. And then lastly, this covalent compound, methane, it goes from methane just to methane, because we know that covalent compounds do not dissociate. So because we only produce one particle in that solution, our I, or the number of particles that we produced, is only 1. So this Van Hoff factor, or the number of ions that are produced in a dissociation, is something that we're going to be using as a variable when we start to look at something like boiling point elevation. Boiling point elevation, when you look at that word, we're of course talking about boiling point. And then the word elevation, you think rising up. So boiling point elevation is indeed just us increasing the boiling point of a substance in order for it to boil at a higher temperature. Now, boiling at a higher temperature has some benefits in cooking, because if you can boil it at a hotter temperature, your food will cook faster. But the general misconception is that the salt in the water makes your water boil faster. That's not true. It just makes it boil at a higher temperature, so that way we can cook our food a lot faster, or maybe by a couple of minutes. Now, what's more important for us to understand is the equation that we're going to use for boiling point elevation. We've got delta T of boiling, our change in boiling point. We've got this Kb, which is going to be a constant that you'll be given. This is the boiling point constant that is specific to each substance. For the most part, we're going to be dealing with water, but remember, this will always be given to you. We have M standing for molality, or the concentration of a solution. This is also going to be given to you. And then lastly, that Van Hoff factor, or the number of ions or particles produced after dissociation. So boiling point elevation, what we're gonna be using this for is for us to be able to determine if we're given a certain concentration of a solution, how can we, or how will that change the boiling point and or freezing point of a substance? So we have what we're going to talk about is freezing point depression first, where you can change the boiling point. You can also change the freezing point by decreasing the temperature. What you're going to notice again is that the formula is relatively the same, but the only thing that's changing here are maybe some of the variables such as Kf, still a constant, but that value is going to be different for water because we're talking about freezing, not boiling. And then of course, we're talking about the change in freezing point, decreasing that freezing point rather than increasing that freezing point. So we'll keep these two formulas in mind. Of course, these constants and these formulas will always be given to you, but what we need to be able to do is know where to plug in which variable given a certain equation and how we can go ahead and solve some of these problems. So I'm going to stop sharing my screen. We're going to switch over. I'm going to turn on my document camera. And what we're going to be doing is we're going to go through a couple of examples together that are present in your packet, just so I can show you the routine that we're going to go through in solving these types of questions. And then I have some practice problems that I'm going to ask for you to work on the next page. All right, so looking at question number 1, it says that if you placed enough NaCl, sodium chloride, right there, it looks like we have our solute. If you place enough NaCl, sorry, I'm trying to figure out this camera angle real quick, into water to produce a solution with a concentration of 7.13 molal, what would be the boiling point elevation and the new boiling point? And then it gives us the boiling point of water, which is 100 degrees Celsius. So just like anything else, what I always like to do is I like to just look at the information that's given to me in the question. So that way it helps me to just kind of plug some of those variables into the equation. So when we look at our equation, this is what we're solving for, change in temperature. We have our Kb, our boiling point constant. Again, we're dealing with water here. So for H2O, we can see the Kb is 0.512. That's going to be something that we're going to plug into our equation. Additionally, we are given a concentration of 7.13 molal. So my M is 7.13. And then my last part of my equation is the I. The I is that Van Hoff factor, or how many ions we're able to produce in the dissociation of our solute, which is NaCl. So this one might take us to show a little bit of work, or perhaps just, once you get into the routine, you'll probably understand it quite fine. But if we have NaCl here, we know that this is an ionic compound that's going to split into a sodium ion and a chlorine ion with a -1. In doing that, we produced 2 ions. So I'm just going to put my I value equal to 2. So it looks like we have a Kb, we have a concentration, or M, and then we have an I, which is 2. So when I want to go ahead and solve for delta T of boiling, my change in boiling point temperature, I'm going to take the 0.512 value. I'm going to multiply that by my M, which was given to me as 7.13. And then finally, I'm going to multiply that by the I, or my number 2, for the number of particles that were produced. So we'll just take that 0.512 times 7.13 times 2. And what we get is a value of 7.30 degrees Celsius as our change in temperature. So what we see is that our change in temperature, or our delta T, is going to be 7.30 degrees Celsius, meaning we were able to increase the boiling point by almost 7.5 degrees Celsius. Now, what we're going to want to do is find out what the new boiling point is. If we know that our boiling point of water is 100 degrees Celsius, if that's what we're starting at, I'm just going to put BP for boiling point. If we know that our boiling point is 100 degrees Celsius and we were able to elevate that or increase it by 7.3 degrees Celsius, I'm going to add 7.3 to 100. So what I will be able to get is that my new boiling point, by adding an amount of salt with this concentration, is going to have a new delta T, or a new boiling point, of 107.30 degrees Celsius. So you can imagine by adding salt to your water, you can imagine that you're going to be able to increase that temperature by 7 degrees Celsius, which means boom, your pasta is going to be ready about 2-3 minutes quicker. Perfect. What a beauty. All right. So there's an example of boiling point elevation. Now, let's see what we can do with freezing point depression. We're going to look at question number 2 now, where I notice I've already included the equation. Now, what we're going to do is the same process where we're going to take a look at what the question is providing for us. We'll make sure to include that information, and then we'll see what we can solve. If you place NH3 in water to produce a solution with a concentration of 2.93 molal, this little m, what would the new freezing point be? Okay, so we have first our K, sorry, this should actually be KF because we're freezing here. If we look up at the chart that's given to us, we see that the KF of water is 1.86. That's a value that will always be given to you, probably in some sort of chart form like you have above there. So KF is equal to 1.86. Now we have our M, which is our concentration. That's also given. M is 2.93. And then finally, we have the I, or the number of ions produced, or the Van Hoff factor from our solute, which is NH3. Now, NH3 is a covalent compound. And what we discussed is that when you put a covalent compound in water, or you try to dissolve it in water, what that's going to do is that's not going to dissociate into individual ions. We're still just going to have NH3 in our water. So because we didn't dissociate into ions, we still have one full molecule. My I is going to be equal to 1. So what you can imagine now is because we've only got one thing, this is probably not going to change the freezing point as much as maybe something with 2 particles would. But at any rate, let's see if we can confirm that using some actual numbers to prove our point. We have our delta T of F, or our change in freezing point, is going to be multiplied by 1.86. Or 1.86, we're going to multiply that by our concentration, or our M, 2.93. And then we're going to multiply that by 1, our I value. So we'll punch this in, 1.86 times 2.93. Whoops, that's a 6, 2.93. And then we're going to multiply that by 1. And what we see is that our change in freezing point is going to be 5 point, I'm just going to round that to 2 decimal places, 45 degrees Celsius. So what we see is that our freezing point of our water is going to change by 5 degrees Celsius, or almost 5.5. So that's our delta T. Our delta T is 5.45 degrees Celsius. Now, if we want to find what the new freezing point is, our new freezing point is going to be lower than the original, because this is the freezing point depression going downwards. So we know that water starts at 0 degrees Celsius when it freezes, but we've added a little bit of NH3 to it. We're going to subtract that freezing point by 5.45 degrees Celsius, giving us a new freezing point of negative 5.45 degrees Celsius. So we were able to decrease the temperature at which our water is going to freeze by putting the NH3 in it. And in doing so, now it needs to be a lot colder for that water to freeze. So that's why we would sprinkle something like salt or another compound on the sidewalks, because instead of it having to be 0 degrees Celsius for it to freeze, it now needs to be in the negatives, which is much colder than what it originally had to be. So there is the complete work for both of those problems. I hope that this was clear enough for you to follow, and hopefully it's pretty straightforward. Really what it is just dissecting the information given to us in the questions, plugging that into an equation and getting an answer, and then applying it to obtain a new freezing or boiling point. So what I'm going to have you do, just to continue to practice this, is you are going to be responsible for completing page 9 in the packet, where you've got 1, 2, 3, 4, 5 examples. And we'll see how we do. I'll provide you with a key. And that's about it for the rest of this unit. All right, thanks for taking the time to watch this video. Let me know if there's anything I can do for you. You are loved, especially by me. Take it easy.